Others have, do you have any of the classes now? Hello? Hello?
No, sir.
Oh, okay. So yeah, it was 17, but now only 14 that we are here. That's what I asked. Okay, right. So yeah, so before going further into the digital electronics, we'll see about number system and codes, right? So we have already seen this one in your second year, I think, right? But we'll quickly recollect that one, right? Right, number system and codes, right? A number system, right, is actually similar to our decimal number system, what we are using to count, right? For example, if you have 121, right, the position determines the value of number, right? The value of this one and this one are not equal, right? So since it is a decimal number, this is 10 to the power 0th position and 10 to the power 1, and this is 10 to the power 2, right? So this one, the value of this one is 10 to the power 0 is 1. So the value of this one is actually 1, right? At the same time, value of this 2 is actually 2 into 10. Am I right? So because 2 to the 10 to the power 0 is 1, so 1 into 1 becomes 1. Here at 10 to the power 1th position, we have our 10th position, we have 2. So the value of this 2 is actually 20. Right? Similarly, the value of this one stands 1 into 10 to the power 2, which is 100, right? That is 100, right? So all together, right, at the end, 100 plus 20 plus 1 will be 121, right? Since the decimal number system is the commonly used number system, we never use that DEC, right, to determine or to denote the number system, right? But we have other base number systems as well. For example, we have binary number system, we have octal number system, we have hexadecimal number system and all, right? So this is a number system, right? Then what is a code? Code is actually, right, you could have remember, right, when you are at school, we might have write the names, for example, A1, B2, C3, D4, right? And maybe so something like this, right? And so on. For example, if the word is ADD, add, right? So we simply write it as 144, right? In this 144, the position does not determine the value. Am I right? These 4 and these 4, they are same and they denotes the English letter D. Clear? So this is a number system and this one is a code, right? In number systems, the position matters, right? In code, it independent to the position, right? It's not depends to the position, right? So if it is just substitute the value and then get it directly, right? So these are the difference between number system and codes, right? We'll see about binary numbers, right? We have studied a lot about binary numbers. Right, binary numbers are the number system with a base of 2, right? Base 2. If the base is 2, I can have 2 numbers, which 0 and 1, right? Similarly, since the base is 10, we have 9 digits, right? 1, 2, up to 9, sorry, 0. We have to start from 0, right? 0 to 9, right? 10 will be 10 to the power 1 and 10 to the power 0, right? So if we have 10 base number system, we will have 10 different digits, which is started from 0. If the base is 2, then we have 2 digits. One is 0 and the other one is 1, right? Yeah. So yeah, I think hope you know, right? So how to convert for example, 31 decimal number, right? If you want to convert this one into binary, what you have to do? Yeah, successive division, right? 2 divided by 2 becomes 15 and I have 1 balance. Am I right? 30 plus 1. Then again 2. I have 7 and 1 balance. Again 2. I have 3 and 1 balance. Again 2. I have 1 and 1 balance. Again 2. I have 0 and 1 balance. You have to do it until you are getting a 0. Then write the balances from bottom to top. Right? So the number will be 1, 1, 1, 1, 1 decimal. Sorry, binary, BIN. Right? It is not 11,111. Right? It is 11111 binary. Clear? 11111 binary. Right? You cannot say it as 11,111 binary. Okay, that number system is only applicable for decimal systems. Right? Similarly, if you want to convert a 1011 binary into decimal number, it is simple, right? So this is called as LSB, right? Least significant bit. And this one is MSB, most significant bit, right? This will be 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3, right? What we have at 2 to the power 0th position? 1, right? So 2 to the power 0 is again 1. So 1 into 1 plus 2 to the power 1 is 2. 2 into 1 plus 2 to the power 2 is 4, but 4 into 0 becomes 0. Plus again 2 to the power 3 becomes 8. 8 into 1 is 8. Right? So if you add it together, 1 plus 2 plus 8, which is 11. Clear? So 1011 binary is equivalent to 11 decimal. Right? 11 decimal. Right? So this is our successive division, and then you can add the values for the positions. So you can easily get the value of numbers. Right. Now we have we may have another number system with a base of 4, right? Quadric number system, right? 4, base 4. Right. With base 4, we may have 0, 1, 2, and 3. Right? 4 numbers which are 0, 1, 2, and 3. Right? The same thing. Right? If you want to convert 65 into a 65 decimal into a base 4 number system, just divide that by 4. If you want to convert it into binary, you have to divide that by 2. If you want to convert it into base 4, then for octal number 8, hexadecimal 16. The procedure is same, but the number which you are going to divide depends on the base. Okay, right. Here 4 means 64, 16, right? 16 and 1 balance. 4, 4 and 0 balance. 4, 1 and 0 balance. 4, 0 and 1 balance, right? Divide it until you get 0 or until you get 1 here, but you have to write the number from here, or you can write it something like this. Right? So this will be 1, 0, 0, 1, right? From bottom to top and quad. Right? This is 1, 0, 0, 1, 4. Similarly, 3, 0, 2, 1 quad. If you want to convert this into a decimal number, sorry, decimal number, again, this is 4 to the power 0, 4 to the power 1, 4 to the power 2, and 4 to the power 3. 4 to the power 0 becomes 1, right? So 1 into 1, 1 into 1 plus 4 to the power 1 becomes 4. So 4 into 2 plus 4 to the power 2 becomes 16 into 0 plus 4 to the power 3 becomes 64 into 3. Clear. So finally 1 plus 4 into 2, 8 plus 0, 64 into 3, 16 into 3, 180, 192. Right. So final answer is 201 decimal. Right. So this is equal to 201 decimal. Clear. Right. Now, see, we have binary number system which has base of 2 and quad number system which has base of 4. Right? I can easily say that 4 equals 2 to the power 2. Am I right? 4 equals 2 to the power 2. Right? So if I want to convert right. So what I can say is, right, I can represent a single base 4 number using a 2-bit binary number. Clear? 2-bit binary number. For example, 0, I can write it as 0, 0. 1, 0, 1. 2, 1, 0, and 3, 1, 1. Done. Right? And now you have asked to convert 3302, right, quad, right, this number into a binary number, right, this number into a binary number. And look at here, each base 4 number can be represented by a 2-bit binary number, right? So now what I can do is I can represent each number by a same 2-bit binary number, right? For 3, it will be 1, 1. Again, I have 3, 1, 1. I have 0, which is 0, 0. 2, which is 1, 0. Right? So my final answer will be 1, 1, 1, 1, 0, 0, 1, 0, 1. Right? So if you want to, since 2 is, right, 4 is 2 to the power 2, only we can use this one. Right? If you want to convert a base 4 number into another number, then you need to convert it into decimal and then convert it into the other base number will be easy. Right? But since we have 4 as 2 to the power 2, we can easily have this one. Right now, you can decode this one, right? 2 to the power 0, 2 to the power 1, 2, 3, 4, 5, 6, 7. Right? Similarly, 4 to the power 0, 1, 2, 3. Right? So, you will end up in the same answer. Right. Now, base 8. Eight, octal number. Right here, we have 0, 1, 2, 3, 4, 5, 6, and 7. Right? And 7. The division is similar, right? For example, 72, what you have to do is you need to successive division. You have to do successive division by 8, right? So 9 into 8, 72, right? But I have 0 balance. Am I right? 9 times and 0 remaining. If I do it 8, then 1 is my, and then I have 1 balance, right? 8 and plus 1. So I can write it like this. Or I can divide this one and made it 0, 1. So my number is 110 OCT for base octal number, right? You can use So 72 decimal is equals 110 octal, right? Similarly, right, this is 8 to the power 0, 8 to the power 1, and 8 to the power 2. 8 to the power 0 into 0, right? 1 plus 0, 0. So here, 8 to the power 2, which is 64 into 1 plus 8 into 1, which is finally 72. Clear? Right. Again, now we can use the same thing what we have seen earlier, right? Which is 8 equals 2 to the power 3. Right? So what we can do is we can represent a single octal number into a 3-bit binary number. 3-bit binary number 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right. Now, if you have asked to convert 1760 OCT into a binary number, what you can simply do is you can represent each bit by these 3-bit binary equivalent. Right? We can do it only because 8 equals 2 to the power 3. Otherwise, we cannot do it, right? So this becomes 1 means 0, 0, 1, 7 means 1, 1, 1, 6 means 1, 1, 0. Again, 0 becomes 0, 0, 0. If you have any zeros in the front, you can leave them, but you cannot leave any zeros at the end. Clear? So this becomes 1, 1, 1, 1, 1, 1, and 4 zeros. Binary. Clear, right? So this is only possible. Again, if you ask to convert this binary number into octal number, what you can do is you can divide them into threes, right? You can group them into threes. 1, 2, 3. And if you have any numbers at the beginning, just add zeros to complement it. And then write down the equivalent numbers. 0, 1, 1, 0 is 6. 1, 1, 1 is 7, 0, 0, 1 is 1. So this one, right? Vice versa. It is simple. Now we'll see about hexadecimal numbers, which is one of the important number system used in computer programming, right? Hardware programming. Hexadecimal number system is with base 16. Right, base 16. So we have 16 numbers starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And to represent 10, we have capital A. Right, 11 we have B, 12 C, right, 13 D, 14 E, and 15 F, right? 15 F. That's it. So 1 to 9 and then A, B, C, D, E, F, right? So for example, if you have a number A, B, 0, 1, right? And if you want to convert it into a decimal number system, so this is 16 to the power 0, 16 to the power 1, 16 to the power 2, 16 to the power 3. Right? 16 to the power 0 is always 1, right? Any number to the power 0 becomes 1, right? 16 to the power 1 is 16. 16 to the power 2 is 64. Sorry, 16 into 16, 256, right? Yes. And then 256 into 16 will be 16 to the power 3. right? So I can say that, yes, so 16 to the power 0 is 1 into 1 plus 16 into 0 plus 16 into 16, 256, right? 512 is 29, yes. 256 into what is B? 11, right? Plus 16 to the power 3 is actually 2 to the power 3, 4, 12. 4096, right? Into A is 10, am I right? A is 10. A stands for 10. So I would say 1 plus 256. Right, 256 into 11, right? 256, 2, 5, 6, right? 6, 1, 8, 2 plus this is right. So add these all together, you will have AB01 equivalent to the decimal number. Okay, right. Now, what is 16? Equal to 2 to the power 4. Right, 2 to the power 4. So each hexadecimal number or base 16 number can be represented by a 4-bit binary number. Right, 4-bit binary number 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Again 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Clear. So this is the binary equivalent of each of the hexadecimal digit or number. Clear. Right. Now, if you have 1, 2, AF hexadecimal and you have asked to write down this number into a binary number, what you can do is each you have to represent with the 4-bit binary number. 1 will be 0, 0, 0, 1. 2 will be 0, 0, 1, 0. A will be 1, 0, 1, 0. F will be 1, 1, 1, 1. Right? The whole term without these zeros in front. 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1. Right, so this is the equivalent binary number, right? So this should be hex and this should be binary. Okay, this is hex and this is binary. Right, now assume that you have a binary number, right? 1, 0, 1. Right, the whole number. Now you are asked to convert this number into a hexadecimal number. Right, you are asked to convert this into a hexadecimal number. What you have to do is you need to group them in 4s, but from your right hand side, which is from your LSB, right? From your LSB, right? Right, so 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then you have two numbers, just add 2 zeros in the front, right? The number does not change when you add zeros in front of the binary number. Sorry, right. So now write down the equivalent hexadecimal from this one. Write 0010, which is 2, 1101, which is D, 1000, 8, 0111, 7, 1100, C. Right? So your number is equivalent hexadecimal number is 2D87C hex. Right? 2D87C hex. Right? So if you have any doubts on these number systems and converting it into binary and converting a binary number into a hexadecimal, octal, or binary quad number, please ask me now. Any questions?
No, sir.
Right. So I can move it into the next. Right. Now we'll see a few codes. Right. We have seen about number systems. Right. So we can see a few codes. The first one is BCD code, binary coded decimal. Or simply BCD. Right? Binary coded decimal. Right? See here, if you want to convert a hexadecimal number into a binary number, what we have done is we have simply represent them by the equivalent 4-bit equivalent binary number. Right? So in BCD, what we are doing is, see here, binary coded decimal. Right? Binary coded decimal. So we have decimal numbers which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are my decimal numbers. So how many numbers we have? 10, right? Okay. Now my question is, you have 10 numbers and you are asked to represent each of them by a binary number. How many bits you need?
4 bits.
Yes, you need 4 bits, right? For example, if you have only 7, then just 3 bits is enough, right? If you have the 8th one, of course, you need the 4th bit, right? You need the 4th bit. What is the maximum decimal number you can write with 2 numbers, 2 digits? What is the maximum decimal number you can write with 2 digits, 2 numbers? No answer. 99, right? 99, am I right?
Yes, sir.
Yeah, but if you want to represent 10 or 99, you need 2 numbers. Am I right? Am I right? If you want to represent 10, also you need 2 numbers. If you want to represent 99, also you need 2 numbers. Right? That's what's happening here. Until 7, you need 3 bits. But for the 8, you need the 4th bit. And 9 also, you need the 4th bit. Until 16, you can use it 4th bit. But any number beyond 9 is useless. Right? Is useless. I'll tell you how. Right, so using a 4-bit equivalent, I can write it as like this, right? 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1. Clear, right? Now you have a decimal number 1985. right? This is a decimal number, right? What you can do is you can represent each of the decimal number with this code, right? With this code. This is similar to what we are doing in our year 1, year 2, right? A for 1, B for 2, C for D, right? Like that, right? This is what we are doing. We are just representing each of the number directly to the binary number, right? For example, we need to represent 5 with 0, 1, 0, 1. For 8, it is 1, 0, 0, 0. For 9, it is 1, 0, 0, 1. For 1, it is 0, 0, 0, 1. Again, you can remove any zeros in the front. So this will be 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, B, C, D. Right, so this is not a number. This is a code. If you want to decode it, again, what you have to do is you need to group them into 4 from your right hand side, right? That, and then this one, and then this one. If you left any bits in front, just that many zeros you need, then write down the equivalent decimal number, right? 0, 0, 0, 1 is 1, 1, 0, 0, 1 is 9, 1, 0, 0, 0 is 8, and 0, 1, 0, 1 is 5. So it's decimal. Clear, right? So this is a code, right? BCD. And we have another few codes, right? Like gray code or XS3 code, right? But I can talk about them whenever it is needed, right? We'll do about, we can use the XS3 code in the logics and all, right? So whenever we need, I will talk about it, right? So just BCD is enough for you now, right? So we'll see about the other codes when we are progressing. Okay, right. Any questions? Any doubts? Please ask me, right? If you miss one chapter or one section, you cannot continue with the other sections. Okay, that's why I am just asking you after every single chapter, right? If you need any help or any clarifications, just ask me to repeat. Right? Okay, now I am asking you a question, right? Okay, before going into that, do you know what is this? Sorry, like this, right? Do you know what is this? I can show you how this works in our next class, right? I will connect the circuit and show you how we can design a circuit, right? This is a 7-segment displays, right? It has 7 segments. See here, you can see it clearly, right? So, oops. Right, so it has, okay, with this dot, it is 9 segments. Now, just neglect that dot, right? So we have 7 segments. Right, we have 7 segments. Am I right? So let me name it as A, B, C, D, E, F, and G. Right? We have 7 segments. Right. Using this 7-segment display, you can display a decimal number. Right? You can display a decimal number from 0 to 9. Right? From 0 to 9. For 1, actually, we will be illuminating these two, right? Not E and F. It should be E and F, right? So this will be your 1. This will be 2. Right? You have digital clocks. You can verify that one, right? This will be your 3. This is your 4. This is your 5. This is your 6. This is your 7. 8 is again, I have all the steps. And this one will be my 9. And of course, I need to start with a 0. Right? I need to start with 0. Clear, right? So this is my 7-segment displays. Right? For example, right? Each of them are LEDs. Right? Each of them are LEDs. See here, you can see that each segment have a light emitting diode. Right? If you apply a voltage at that pin, then that section will be illuminated. Right? If you apply a voltage in that section, that will be illuminated. Right. 2, if you want to show 1 in your display, then you need to illuminate segment C and segment B. Am I right? If you want to show 1, then you need to eliminate section B and segment C. If you want to eliminate 9, then you need to eliminate B, C. Except F, you need to eliminate all the other segments. Am I right? A, B, C, D, E, G. Right. Now, okay, my question is design a BCD to 7-segment display converter, right? 7-segment display circuit, right? So which means you need to design a circuit, right? This is the circuit, right? Which the input should be a BCD number. How many bits you have for a BCD number? How many bits you need to represent a BCD number?
4 bits.
Yes, 4 bits means you will have 4 input lines. If that be A, B, C, and D. Am I right? Right. If you want to eliminate these segments, how many outputs you need to have? How many outputs you need to have? No. Right. How many segments you have here? How many segments you have? 1, 2, 3, 4, 5, 6, and 7. Am I right? So you need 1 each line to shine each of the LEDs in display. Am I right? Am I right? Yes. So I need a total of 7 output lines. 2, 3, 4, 5, 6, 7, which is small a, B, C, D, E, F, and G. Right? So I have 4 inputs and 7 outputs. Right? Now, what I have to do is I need to draw a truth table. I need to draw a truth table. What is a truth table? What is the definition of the truth table? What is the definition of a truth table? Yeah, a truth table consists all the possible inputs and outputs, right? So this is a BCD number, and here I'm going to connect each of them using the pins at the back here, right? You can see each pins, right? So 1, 2, 3, 4, 5, and there is a ground, right? And then 0, right? That's why we have 10 pins here, right? So like this. So there are 7 pins will be coming here, and 1 common ground goes there, right? Don't worry about it. But we need a circuit to show this one. Right, so now we need a truth table. Right, so a truth table, as I said, you must have all the possible inputs. What are the possible inputs? A, B, C, and D. And all the possible outputs. What are the outputs we have? A to G, A, B, C, D, E, F, G. Right. So first, yeah, since we have 4, I can write it as 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, right? And then goes on. Right. Now, if my input is 0, 0, 0, 0, right? If my input is 0, 0, 0, 0, which is a binary equivalent of 0, am I right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this is 10. Am I right? Am I right? Of course. If I give 0, 0, 0, 0 as the input, what should be my output? What should be my output? Right, look at here. To represent 0, except G, right? Except G, all the other segments need to be eliminated. Clear? All the other right? All the other segments need to be illuminated. Am I right? So elimination means 1, right? What is 1 stands for? A 5, right? A high voltage, right? So for 0, 0, 0, 0, except G, all the others should be 1. Am I right? So this will be 0, 1, 1, 1, 1, 1, 1. Clear? Right. If I give 0, 0, 0, 1 as the input, what will be my output? What should be my output here? What should be my output? Please unmute and speak.
B and C.
Right. B and C should be illuminated. Right. And all the others will be off. Am I right? So B and C are 1 and all the others are 0. Clear? Likewise, you have to complete the truth table when you are coming tomorrow. Not tomorrow, maybe tomorrow is Thursday, no? Today, Wednesday? Yeah, tomorrow, Thursday. Yeah, we may have class tomorrow morning, right? At 9 o'clock. Do you have any class at 9? Do you have class at 9? Okay, so I'll schedule a class at tomorrow 9. So when you are coming tomorrow, just complete this one, right? Look at here. I am using a BCD number, right? What is the maximum BCD number we can have? What is the maximum number we can have? 9, right? Which is this one. But when you are drawing the truth table, you need to have until 15, right? You cannot stop with this one, right? You need to continue until 16. Okay, right? And then you complete the truth table with all the possible outputs and inputs, right? Yeah, we can see tomorrow morning. Is it okay? Shall we have the class tomorrow morning?
Okay.
Right. So you guys take a maths copy sheet of your brothers or sisters in your home and then write down the truth table with all the possible inputs and outputs. Complete it before you are coming for tomorrow's class. Okay, we'll continue further tomorrow morning at 9. Right? Do you have any questions? Right. So if you have no questions, we can wind up the session. Right? Okay. So see you tomorrow at 9 o'clock. And please make sure all of you should talk tomorrow, right? Not only one student. I want all of you to speak up, right? Otherwise, teaching digital electronics online is a horrible experience for me, right? So please try to speak tomorrow. Bring a pen and paper while you are attending the class. Okay. Right. Thank you.